Okay, so having talked about some systems of ODEs and how to solve a very specific example, I want to talk about some applications of this idea so that you can see why one might want to learn this more complicated business of systems of ODEs. Let's talk about the following application. Let's talk about applications. So here's an example, and it involving our very favorite uh, type of problem, mixing problems. Okay, so it's the mixing problem that are back. But now this time, instead of just thinking about a single reservoir, I want to think about two tanks which are connected to one another. So let's say that we have two tanks with brine. We'll call these tank one and tank two. With brine flows from one to the other. Let me just go ahead and draw a picture right now. So we're going to have tank one here. I'm not a very good drawer, so just deal with it. Here's tank one. And there's a sort of tank two over here, maybe on the side next to it. Now what I've got to draw is a complicated piping system in which solution in tank one will flow into tank two, and also solution in tank two will flow into tank one. So we've got sort of outflow here, and then it's going to go up like this and flow into tank two, like this. Okay. And then we're going to have outflow from tank two, and it'll pass underneath here, so I'll indicate that in this way, and then flow into tank one. Hopefully this isn't too confusing. Okay, so we've got solution going from tank, here's tank one, and here's tank two. We've got solution inside each, like this. Okay, hopefully this is, hopefully you can understand what's happening here. All right. The idea is that we're going to have, let's say that the volumes of solution in each are the same. So suppose that we have V liters of solution in each tank. And let's say that the rate at which stuff is flowing from one tank into the other is the same. So we have the outflow from each tank is R liters per minute. Both tanks is R liters per minute. Okay. And that outflow goes immediately into the other tank. Does this make sense? But we will call the amount of solute, in this case the solute is salt, since this is brine. Brine is just salt with water. Let's call x1 the amount of salt in grams in tank one. And we'll call x2 the amount of salt in tank two. And right, we're measuring this in grams, so I'll indicate that like this. The units on x1 and x2 are grams. Okay? Okay, then what we want to understand, or what we want to do now, is set up a differential equation or a system of differential equations for x1 and x2. x1 and x2 are our dependent variables. Our independent variable here is going to be time. So we want to think about what are x1 prime and what is x2 prime. So as usual, we'll use the idea that in these that is very often done in these mixing problems. We're going to think about the rate at which salt is entering minus the rate at which salt is leaving. So let's just think about x1 prime, for example. This is the rate salt enters tank 1 minus the rate salt exits tank 1. Right? Rate in minus rate out. That's all I'm saying. Okay? Well, what is the rate at which salt is entering the tank? So the rate at which salt is entering depends on the concentration of salt in tank 2. The concentration of salt in tank 2 is given by the volume. Well, so it's given by two things, right? We need to know two things in order to figure out this concentration of salt in tank 2. We need to know the amount of salt in tank 2 at any particular time, and we need to know the volume of solution in tank 2. Volume of solution we know is V. It's V liters of solutions in each tank. That's indicated by this line here, right? So we know the volume, and that's no problem. The amount of salt we define to be x sub 2. So the concentration of salt in tank, the concentration of the brine in tank 2 is going to be given by x sub 2 divided by V. Okay? Remember, I'm thinking about x1 prime here. Now, that's just the concentration. We also need to know the rate at which this solution, which has this concentration, is flowing into tank 1. And that rate is R. Did I write that? Yeah, R liters per minute. You can see that here. R liters per minute. Okay? So we're going to take x2V over V times R. Then we're going to measure the rate at which salt is exiting. That's going to be, well, we want to know the concentration of solution in tank 1. That's x1 over V, multiplied by the rate at which solution is leaving tank 1, and that's R. And if we simplify this, this becomes R over V times x2 minus x1. That's x1 prime. Similarly, x2 prime will end up being R over V, x1 minus x2. It's a totally symmetric kind of situation, so you can just swap out the subscripts. And so what this gives us is this pair of equations. I'll write them down again here. I don't know why I'm doing this again, but just to organize it for ourselves. x1 prime is R over V times x2 minus x1. And x2 prime is equal to R over V times x1 minus x2. And here is our system of differential equations, the first order system. Okay? Now, it should be said that you can't, like in the previous example that we did at the end of the last video, you can't solve for one of x1 or x2 separately and then plug it into the other equation. That there really is a kind of, you need to know x1 and x2. You need to solve for these kinds of things sort of simultaneously. And of course, what we're going to learn in the coming days is precisely how to do that. This is sometimes referred to as coupling. X1 and X2 are coupled quantities in this problem, okay? And so we're going to learn how to do that, but it's going to take some work, okay? And so that's the kind of work that we're going to be doing. Another thing I want to say about this before we leave this is that, well, yeah, let me say it like this. This is what's called a linear system of equations. Sorry, my brain just went, sorry. I don't know why I'm apologizing. Okay, whatever. This is what's called a linear system of equations. What, right? And I hope that you have that sense now. So look at, for example, this first equation. X1 prime is equal to R over V times X2 minus X1. I want that to feel linear to you. Yes, this R over V is a constant, okay? That's a constant, so that's not a big deal. But the fact that we don't see terms in here like X1 times X2, we don't see like X2 squared, we don't see like sine of X2 or sine of X1 or anything like that. It's just these terms are sort of separated and there's only one instance of them in these equations, suggests that this is a first order linear system of equations. Okay. Okay. Now, one might ask, what is going to be what's the solution to this? What is x1 and x2? And I won't answer that question now. We'll learn techniques to do that. But one could probably, through your just sort of common sense, figure out some things about what should happen in the long run. The equilibrium solution, the long-term equilibrium solution to this, when we go way far out into the future. Because one thing that you can realize is that X1 and X2, the amount of salt in tank 1 and the amount of salt in tank 2, even though those might be changing with time, X1 and X2 might change with time, you know what won't change with time? Is their sum. X1 plus X2 is not going to change because there isn't some external, there isn't an external source of brine which is messing with the total amount of salt in these two tanks. So X1 plus X2 won't change with time. And I think what your common sense would suggest is that as time gets very, very large, you're going to see the amount of salt in each of the tanks equalize, right? So that the amount of salt in tank 1 will be x1 plus x2 over 2, basically half of the total amount of salt. And similarly for the other tank, right? So whatever solution we do find, we should expect to see that common sense phenomenon revealing itself in the mathematics of the solution, okay? But that's for another day. Again, we're not going to solve this now. I want to talk about another example. This is a second order example. Let's consider where we have, this is kind of related to the harmonic oscillator stuff, but now instead of there just being a single object, let's think about two movable objects attached to a spring. We're going to keep it a one-dimensional problem in the sense that these things are only going to have 1 degree of freedom of motion. Here's the idea. We're going to imagine two kind of carts on a rail. So something like this. We're going to have a cart 1. This will have mass m1, and it's attached to a second cart, m2. And these things are on wheels. And these wheels are on some kind of frictionless surface, okay? And this spring, this is a spring in between these, is going to have a restored, it's going to obey Hooke's law. We'll call that constant, the spring constant, K, as usual, okay? And let me define so imagine that you take this system, you just place it on this frictionless rail, okay? And it's at rest. So it's not oscillating. The spring, there's no forces acting on anything in any meaningful way. We're going to call the positions of cart 1 and cart 2, the equilibrium position, we'll call that x1. And so this will be x2. And we'll imagine that each of these are displacements from the equilibrium position, x1 and x2. Okay, and we'll take the positive direction to be this way. This way is positive. Okay. All right. So I think that what we can do is set up a system of differential equations using something like Newton's law together with Hooke's law. So for example, we can say that if we look at x1, so if we think about the acceleration on the first cart, and we look at m1 times x1 double prime, okay? So I'm thinking about Newton's second law, F equals ma. This is ma for the first cart, and so that should be equal to the force, the total net force acting on the first cart, okay? Now, for that first cart, what is the force acting on it by Hooke's law? Well, you're going to take x2, which is the displacement. You basically need to measure how much this this spring is sort of being either extended or contracted, and then you're going to multiply that by k, right? You work out the mathematics of this, and what you're going to get is that this should be equal to k times x2 minus x1. I hope I have that right. Yeah. This is right. And similarly, thinking about the second cart here, we're going to have m2 is equal to x2 double prime. M2 times x2 double prime is equal to k times x1 minus x2. Yes, that's right. So this is a second order equation, second order system of equations. Which is sort of very much related to the harmonic oscillator stuff that we've been doing in our first explorations around ODEs. Yeah. Okay, that's enough for this one. In the next one, we'll talk about some issues related to how to reduce many complicated problems, like for example, this second order system into a system of first order equations.